Hi, in this video, we'll be going through and diving deeper into the solutions for a boundary value problem. And specifically, we'll be talking about the eigenvalue problem. So what do I mean? Well, let's see. So with the previous example, in the previous video, we have this eigenvalue problem and we have a boundary condition which is y0 equals to 0 and y prime equals to 0. Y pi equals to 0. And we computed the eigenvalues to be n squared and sine nx for the eigenfunctions. What we observe is that the real eigenvalues are always positive since it's n squared, and that the eigenfunctions are mutually orthogonal. What does two functions mean to be orthogonal? Well, the integral of the product is 0. And for each eigenvalue, there will only be one eigenfunction, meaning the space is one dimensional, or you can say that the eigenvalue is simple. So we see these are the properties of the eigenvalues and eigenfunctions after solving explicitly what are they. But actually we can prove that lambda is positive without any explicit solution. So let's just see how we prove this set of observations without finding it. And we see that, okay, so we have the equation y double prime equals to minus y lambda, minus lambda y. So if we assume that lambda is an eigenvalue with some eigenfunction, then we take the inner product of this thing with y. Okay? But we know that minus y double prime is lambda y, and when we take the inner product, it will just be, you can take out the lambda at the same time. It won't really affect the solution. Okay, so from there, we got this portion equals to the product over here. Okay, we'll look at it. We got the product over there. Then how do we solve this? Well, we can use the integral by parts and actually show that it equals to integral from 0 to pi of y prime y prime conjugate minus y prime y conjugate sub in 0 and pi. Well, this we can use the boundary condition to actually show that it equals to 0. And for this side, well, it has to be larger or equals to 0. Okay? And then we look at this portion. We look at it here, and then we show that the inner product of y and y is just gonna be this function. And because this is the modulus, this whole thing must always be positive. This means that lambda must equals to minus the inner product here divided by the inner product here. Since this is always positive, this will be real, and this portion is larger or equals to 0, means lambda must be larger or equals to 0. So that this is defined, so lambda is real and lambda is larger or equals to 0. Now we just need to show that the lambda cannot be 0, and to do so, we just say that if this is 0, then this portion must be 0. So if the numerator inner product is 0, then it actually shows that because the numerator inner product is just this, okay? So for this to be 0, it must mean that y prime equals to 0. If we combine that with the boundary condition, because y prime is identically 0 everywhere, and you know y0 is 0, we actually get that y is 0 throughout the entire interval. But y has to be a non-trivial eigenfunction, so this is a contradiction, which means that this inner product has to be strictly positive, which implies that lambda is larger than 0. So that's one proof of it. For the next one, we want to show that they are mutually orthogonal. So we just assume that we have two non-trivial eigenfunctions. Then we just so because they are both the eigenfunctions, they satisfy the equation over here. If we take the inner product of the top one with y2, we get y1 times the inner product of y1 and y2, and for the bottom we inner product with y1 instead, and we get lambda 2 times the inner product of y1 y2. Okay, so what we do is we subtract them. So you just need to get used to the techniques of solving it, and it's quite repetitive. So you just subtract them. You see, this part and this part is the same. So when you subtract them, it's y1 minus y2. But because they are different, they are corresponding to different eigenvalues, then this part cannot equal to 0. Okay, that's fine. For here now, we get this minus this. We can combine it over here, and we can integrate by parts over here to actually get this very long expression. But if you, without careless mistake, you should be able to get this. And when you sum in every value, this part will just cancel each other. So this part is gone, this part is 0 0, so everything is 0. Then this must mean that the integral, because this is non-zero, the integral must be 0. So this shows that the inner product is 0, so they are mutually orthogonal. And to sidetrack a bit, to talk more about the interesting facts, is that for Fourier sine series, because we have shown that the family of these eigenfunctions sine and x are orthogonal, the fact remains that any continuous function from 0 to pi can be expanded using this as the orthogonal basis, and this is known as the Fourier sine series. So the last observation is that we actually showed that all the eigenvalues are simple. So let's just say you have one eigenvalue already, and this eigenspace is more than 1. So let's just say 2. You have 2 eigenfunctions corresponding to lambda. Then we want to show that actually the y1 and the y2 are linearly dependent on each other. That means their Wronskian is 0. So to find the Wronskian, you just find the determinant of the matrix here, and with that, you already know when you sub in 0, y1 is 0 0, so this card cancels out. Then this part you don't know, but it doesn't matter, because once you know this is 0, when you take the product, it's 0, and that actually just shows that y1 and y2 must be linearly dependent. So the space of the eigenfunction is just one dimensional. So you can see how we were able to find properties of the eigenvalue and its eigenfunction without actually explicitly finding the solution to the eigenvalue problem. So even with a more complicated boundary condition like the following here, we can use the same technique. So first, we let minus y double prime equals to lambda y, because this is how the eigenvalue problem looks like. And then we take the inner product with y. One side must be larger or equals to 0, while the other side is strictly larger than 0. So lambda, this part, you just divide over. You have this equals to this whole chunk divided by this, which has to be larger or equals to 0. So you already just showed that it is real. Now to rule out the case that is 0, well, you just say that if this is 0, then this left hand side integral must be 0. So this part must be 0. Then after that, well, for this whole thing to be 0, well, you just look at it. Okay, so if the left hand side integral is 0, then we need both. This is always positive, so this has to be 0 and this has to be 0. Okay, so for this to be 0, then y1 must be 0 already, so that means y prime 1 must be 0. Okay, and for this to be 0, it just means that y prime must also be identically 0 throughout. And so this means that y is a constant, but we know y0 is 0, so y is 0 throughout, but this contradicts the non-triviality of y, so lambda must be larger than 0. So you can see how it's exactly the same thing. You just take the inner product with y, because here got y. When you inner product y, you can take out the lambda and get a non-zero here. So this is some number that will confirm be defined. Now we can also show that there are infinitely many eigenvalues to this example. So okay, so we have shown that all the eigenvalues are real and positive. So we let lambda be larger than 0 and the characteristic equation be the following. We can find the general solution to it. Because we know lambda is positive, this part must be a complex number already. So we just find it. Then we now can use the boundary condition to determine C1 and C2, which when you sub in 0, you get C1 0, but when you sub in the other boundary condition, you get that C2 equals to this whole chunk. So to ensure non-triviality, this part cannot be 0, so this part must be 0. And for this portion to be 0, okay, you just look at it. That means I have to solve this equation values. So we just let mu equals to square root lambda to make it nicer a bit. And we get that tangent mu equals to minus mu. And from here we can show that there will be infinitely many solutions to this space. As you can just what you do is you just take the interval from 0 to pi over 2, then to pi. So in one interval, in all these intervals, you show that there will be a solution. You just draw the line here, and then you just see cut here, cut here, cut here. So every interval you have a solution. So that's the idea, to show that here has infinitely many solutions. So that's all for this video. I hope you have learned the techniques in approaching these boundary value problems to determine properties of the lambda for the eigenvalue problems. In the next video, we'll talk more properties that we can derive from the eigenvalue problem as we look into more complicated examples. So I'll catch you in the next one, and I'll see you again. Bye!